Next topic is resultant of parallel forces. So we're done now with concurrent forces. We talked about moment because we need moment in taking the resultant of parallel forces. Let's talk a bit about that. Okay. So the resultant of a parallel force system is determined when its magnitude, direction, and position is known. The common characteristics of a force. Now, one of the outstanding differences between a concurrent and a parallel force system is that in the former, position of the resultant is known by inspection, whereas the latter it's not. So concurrent force system, by inspection, we can figure out the direction, which is what we did in one of our examples. Here, right? We guessed or we concluded this is the position of our resultant. Also, we know that resultant acts at the intersection of your forces for concurrent force systems. Okay, resultant always acts at the intersection of your concurrent force system. So that's why it's easy to figure out its position. However, for concurrent force for parallel force systems, that is not the case. We need to solve for more things to find out where the resultant is located. So determine R, select some convenience point O as a moment center, and then use the equation, summation of moment about O equals RD. Where R is the resultant of your parallel force system, and then D is the distance about your moment center O, or about any point of importance. So for parallel force systems, we're not only gonna be talking about point loads. Point loads are what we've encountered so far. Okay, the single forces are called point force or point loads. For parallel force systems, we have what we call your distributed load, as you can see in the figure. So the resultant of a distributed load is equal to the area of the load diagram and is acting at the centroid of that area. So basically, we have these distributed loads, and then the red arrow represents their resultant. That resultant can also mean it is the point load version of your distributed load. Okay, it is convenient whenever we make a distributed load to a point load because it's easier to write our computation. That's why we need to talk about this first. As stated here, point load or resultant is just equal to the area of your load diagram. Let's talk about that. So this is, let's take these figures for example, right? This is a rectangle, right? Area of a rectangle is just base times height or length times width. Therefore, the point load version or the resultant of this load diagram is the same. So it's also base times height. So base is this L, height is denoted by this distributed weight W sub O. So when you see something along the lines of, let's say 10 kilonewton per meter, when you have this unit, that means that is the unit of your distributed load. So that is the value of your height. Okay, or if it's indicated, that's also your W sub O. Okay, so L times W sub O is the equation for your resultant, or it's more commonly written as your uniform load times base L. Okay, same thing here. We have a right triangle. Area is 1/2 base times height. Doing that here, that's 1/2 base again is L, and then height once again is your W sub O for your distributed load. So it's 1/2 L times W, or it's more commonly written as 1/2 W times L. Okay, and that is how you convert your distributed load to your point load. Okay. Any questions so far before we move on to our examples? Once again, please answer in the chat. Okay, great. So let's have one example so that you have a better idea of parallel forces. Okay. Determine the resultant of the parallel force system acting on bar AB as shown in the figure. So resultant, that means its magnitude and its position. The resultant is easy for parallel force systems. That's just a summation of forces. Here, it's Y. They're all vertical. Sign convention applies. Upwards, positive, downwards, negative. So we have, let's start from the left side. We have downward, so that's negative 20 minus 10 plus 30 minus 40. Please compute. What's the answer? Correct. Rafael Pasagi and Joshua Bongalos. Pasagi. Oh, Joshua David. Okay, negative 40. So once again, this negative sign just indicates the direction. So the resultant is negative 40 pounds or 40 pounds downward. Okay, now we're not done. Usually when we're looking for resultant, we also need its position. Okay, so you're gonna now take a reference point. Let's say A. I'm gonna take reference point A. So you don't know where your resultant is. You can just guess. So for now, let's say usually your resultant is within your system of forces. It's downward, so you're going to draw that downward as well. So let's say here. Okay, I'm going to guess this is where my resultant lies. Okay, and then you're going to use the concept of moment to figure out where that exactly is. So again, I'm going to take reference point A. You can choose B. That's fine. It's not specified in the problem, so it's up to you. So summation of moment about A is equal to summation of forces times distance, right? And then another equation, let's look at our given here. It's also equal to RD, where D, once again, is the position of our resultant. So MA, that's also equal to RD. So RD is equal to summation of our forces. Okay, so let's start again from the left side. 20 directly intersects or passes through A, so I'm going to ignore that. Next, 10, rotate that about A, that's clockwise, therefore positive, then perpendicular distance 2. Next, 30, rotate that about A, that's counterclockwise, negative 30, perpendicular distance 3 plus 2 times 5. And then lastly, B, rotate that about A, once again counterclockwise, negative 40, sorry, that's clockwise, so positive 40, distance 3, 6, 7, 8. And what is R? R is 40. Rotate that R about A, that's clockwise. So that's 40 times, this is what we're looking for, D. Please solve. What's D? Divide by 40. 4.75. Correct, it's 4.75. We got it correct. Michelle, correct. Paolo, correct. We already have 2 points. Yung wala pa. Correct, Naomi. Also. And then, correct is Joaquin. Okay, it's 4.75 unit feet. So dA, to denote its distance from your point A. So to be more specific, 4.75 feet to the right of A. Okay? And that is example number 1 for parallel forces. Any questions so far? Please answer in the chat. Okay, alright, I missed one. My bad. Oh, I don't think it- Okay, what do you mean, Joshua? Zero? Okay. Since you don't have any question, that ends the lecture part of our activity. Okay? So I'm gonna end the recording there.